welcome back to another explainer. Today, we are putting an artificial intelligence brain on a serious diet. We're diving into a really fascinating breakdown from NVIDIA researchers on exactly how they took a massive computationally heavy language model and shrunk it way down. And the crazy part, they did it without losing the model's edge, potentially saving millions in computing costs along the way. So let's jump right in. Okay, let's dive into this. On one side, you have the rather bulky MetaLlama 3.18b model, and standing right next to it is its sleeker, highly optimized sibling, the NVIDIA Minitron 4B. They definitely seem related, right? Well, that's because they are. The smaller one was essentially carved directly out of the larger one. Which brings us to the absolute core of today's explainer. How exactly do we make AI models smaller without making them dumber? We all know that giant models, like the massive Llama 3.1 405B, are just incredible at complex tasks. But man, they come with incredibly heavy computing costs. You literally need massive data centers just to run them. So how do we pack that kind of power into something much more manageable? And that is exactly the heavyweight problem we're facing right now. Big models equal massive resource costs. Deploying them to everyday users is just incredibly resource intensive. Because of this bottleneck, the entire industry is seeing this massive shift towards SLMs, or small language models. The ultimate goal here is to build models that are dirt cheap to deploy, but still highly proficient in tricky language tasks like reasoning, math, and coding. To actually pull this off, researchers rely on a clever technique called pruning. Pruning is, well, exactly what it sounds like, the process of making a model smaller and leaner. You can do this by dropping entire layers, which we call depth pruning, or you can drop specific neurons, attention heads, and embedding channels, which is known as width pruning. Think of it like editing a bloated manuscript. You can either chop out entire chapters, that's depth, or you can go through and meticulously trim unnecessary words from every single page, and that's width. But here's the catch. You can't just hack away at a neural network and expect it to stay smart. That is where our second key concept comes in. Model distillation. This is the technique of transferring knowledge from a massive, complex teacher model directly into a smaller, simpler student model. If pruning is putting the brain on a diet, well, distillation is like sending that newly dieted model to grad school with a master teacher. It makes sure the model actually retains its predictive smarts. Now, there are a couple of ways to actually do this distillation. On one side, we have SDG fine-tuning. This is where the student just mimics the final token predicted by the teacher. Honestly, it's kind of like just giving the student the final answer to memorize. But NVIDIA's framework relies on classical knowledge distillation. In this method, the student mimics the logits, which are the raw mathematical predictions before they become actual words, along with other intermediate states of the teacher. So instead of just getting a one-shot label, the student gets a much richer distribution of feedback. It basically shows the student the teacher's entire thought process. Let's move to how this builds into an actual real-world pipeline. The researchers mapped it out in 3 really clear steps. First, you estimate the importance of each model component using a small 1024 sample calibration dataset. Second, you rank those components and physically trim the model down to your target size. And third, you perform a light retraining phase using that classical model distillation we just talked about. And the way they apply this is just a brilliant iterative process. They didn't just blindly jump from 15 billion parameters straight down to 4 billion. No, they started with a 15B model, estimated, trimmed, and distilled it down into an 8B model. Then, they took that brand new 8B model, made it the new starting point, and systematically trimmed and distilled it again down to the 4B Minitron that we're looking at today. But wait, how do they actually know what to cut without completely ruining the model? Well, they use something called activation-based importance estimation. The big takeaway here is that it's highly cost-effective. By running a tiny amount of data through the model, and specifically using only forward propagation passes, they analyze the activation data to see which parts of the neural network are doing the heavy lifting and which parts are just dead weight. This entirely avoids the massive computing drain of backward propagation. Through all of this intense testing, NVIDIA essentially wrote a golden rulebook for model compression. The main takeaways? Always train the largest model first. Strongly prefer width over depth pruning for anything under 15 billion parameters. Stick to single-shot importance estimation, and retrain exclusively using distillation loss. It really is a remarkably clean, efficient roadmap for anyone looking to shrink a model down. Now, what's really interesting is what happens if you ignore those golden rules and try to aggressively depth prune anyway. When mapping out layer importance, you see massive spikes in loss at the very beginning and the very end of the model. That tells us something absolutely crucial. The first and last layers of the neural net are virtually untouchable. If you cut those, the model's intelligence literally drops off a cliff. Actually, scratch that. It gets a little bit trickier. See, that raw language model loss we just talked about doesn't perfectly correlate with downstream accuracy on actual real-world tasks, like the Winter-Grande benchmark. By testing different combinations, researchers found that the absolute sweet spot for a 50% depth cut was specifically removing layers 16 through 31. This successfully avoided those hypercritical early layers, as well as the very final layer, layer 32. But even after finding that sweet spot for depth, remember the golden rule: prefer with pruning. When researchers trimmed the model's width instead, the parameter reductions were just massive. They slashed the MLP intermediate dimension from over 14,000 down to roughly 9,200. They pruned the hidden size from 4,096 down to 3,072. They essentially thinned out every single layer of the entire model across its attention heads and embedding channels. And wow, the accuracy payoff for choosing width over depth is undeniable. The Minitron 4B width pruned model is punching way, way above its weight class. It performs incredibly favorably against state-of-the-art open source models of a similar size. It decisively beats out Google's Gemma 2 2.6B and really holds its own against Microsoft's Phi 2, especially when you look at complex MMLU reasoning benchmarks. So why do we even care if it's maybe slightly less accurate than the original 8B model? Well, it all comes down to this number right here, 2.7x. The Debbie-based 4B variant boasts an average throughput speedup of roughly 2.7 times the original 8B model. Even the width-pruned version is nearly twice as fast. They are incredibly lightweight, and man, are they fast to run. Plus, they are incredibly lightweight to actually build. This whole process resulted in up to a 40x reduction in required training tokens. Since you aren't training these models from scratch, each additional smaller model only requires about 100 billion tokens to distill. This isn't just a time saver. We're talking about a massive financial breakthrough for AI development. To sum up the sheer magnitude of this, the researchers' own conclusion really hits the nail on the head. They state, pruning and classical knowledge distillation is a highly cost-effective method to progressively obtain LLMs of smaller size, achieving superior accuracy compared to training from scratch. It really is a massive leap forward in making high-level AI efficient and totally accessible. Which leaves us with a really fascinating final thought. If a meticulously dieted 4 billion parameter model can rival the capabilities of its giant predecessors, what does the future of personalized edge device AI actually look like? When powerful AI can run locally right on your phone or your laptop without needing to ping a massive data center, well, the possibilities are entirely rewritten. Think about that. Until next time, keep learning and stay focused.